What happens when the digital highways that connect our world suddenly hit a roadblock? When that critical link between, say, your headquarters in Dallas and your branch office in London just goes dark. Or maybe when your cloud applications slow way down, just crawl, impacting thousands of users globally. From the cloud right down to your coffee maker, everything is connected these days, and it really all starts with data communications. Today, we're taking a deep dive into the very arteries of the internet, wide area networks, or WANs, and maybe more importantly, how to troubleshoot them when those vital connections falter.
That's a really great way to frame it. WANs, they truly are the backbone of modern business. They enable, well, everything, global operations, remote workforces, the cloud connectivity we just expect now. But, for business students like yourselves, understanding how to diagnose and fix issues on these sprawling networks, it isn't just a technical skill. It's actually a crucial business competency. It directly impacts the bottom line, an organization's ability to compete. So yeah, this deep dive is really designed to equip you with a structured understanding of how to diagnose, how to resolve network issues across these huge distances. We'll try to demystify complex protocols like BGP, and we'll explore the strategic choices in network design too, things that impact performance, security, and frankly, your future career readiness. And we're connecting all this directly back to your BCIS 1347 data communications curriculum, giving you a practical kind of real-world lens on voice and data tech, the hardware, software protocols, and those critical managerial issues, things like design, integration, selection, and the future impact of all these technologies.
Okay, fantastic. And before we really unpack this further, if you're finding value here, if you're learning how to navigate the complexities of data comms and, position yourself for a bright future in business and tech, please take just a moment right now to like, subscribe, and share this deep dive. It honestly helps us bring more of these essential insights directly to you. And remember, you'll find additional resources down in the description below. They can really help you continue your learning journey long after we wrap up today. So, okay, let's start at the beginning. A critical network link goes down, panic sets in. Before we even think about touching a keyboard, running a command, what's our absolute first line of defense? Where do we begin?
That's a great question. And it leads us straight to what many consider the unsung hero of network troubleshooting. Good documentation, comprehensive network documentation. It might sound a bit, well, mundane maybe, but accurate and complete documentation, things like physical and logical topology diagrams, detailed device records, performance baselines. These are your first and honestly most critical tools.
Right. It's like trying to fix a complex machine without the blueprint, isn't it?
Exactly. You just can't fix what you don't understand or, frankly, what you can't even locate on the network. This foundational step, it directly ties into one of your BCIS. Oh, absolutely. That's a brilliant point. Often it's the physical layer documentation that's the weakest link. Organizations might have logical diagrams showing IPs and routing, sure, but when it comes down to knowing exactly which cable runs from port G101 on switch A to port G105 on server B, or even just where that cable is physically routed through the building, that's often where things break down.
Ah, I see. The physical path.
Precisely. So to elaborate a bit, physical topology diagrams should show you exactly where cables run, or devices sit in racks, the specific ports used, the types of connectors, everything physical. Logical diagrams, on the other hand, they illustrate the IP addresses, the VLANs, subnet masks, and the routing protocols in OSPF, BGP, whatever it is, and how they all interact logically. Then you have device documentation. This should be a meticulous record for each network device. Its model number, the operating system version like Cisco iOS version, every single interface, its IP and MMC addresses, which routing protocols it's running, even license details. It all matters. And critically, performance baselines. You absolutely need these. They establish what normal network behavior actually looks like.
How do you establish that baseline?
Well, you collect metrics like interface utilization, CPU load on routers and switches, maybe error rates, over a period of time, usually a few weeks, maybe 2 to 4, but at least 7 days to catch weekly patterns. This creates your benchmark. I remember this one time, before we had solid baselines, a critical link kept slowing down. Not going down, just slow, sporadically. We spent days chasing hardware ghosts, swapping components. Turned out it was a specific large report run automatically every Tuesday morning that spiked the core router's CPU. Baselines would have flagged that deviation immediately. So if something deviates from that baseline later, you instantly know there's an issue, and you can pinpoint where normal has shifted.
That's a fantastic example. And it really highlights something else too, doesn't it? Good documentation isn't just about reactive troubleshooting. It feels like the real insight here is how it democratizes knowledge within the team. It frees up your most senior people from constantly putting out fires, rediscovering things that should just be known, lets them focus on design, innovation, moving the business forward.
Exactly. Without it, you're not just losing time during an outage, you're effectively paying your most expensive staff to constantly solve problems. For anyone in business, understanding this value isn't just technical. Good documentation reduces downtime, speeds up resolution, ensures business continuity. All of that directly impacts the bottom line. These are absolutely critical managerial issues in data communications.
Okay, so we've got our blueprints, our documentation, we know what normal looks like thanks to baselines. What's next? Because even with the best maps, you still need a strategy for the journey, right? The
Yeah.
actual journey of fixing the problem.
Precisely. That leads us directly to mastering the process, using structured troubleshooting methods. This isn't about just randomly typing commands hoping something works, which, let's be honest, can feel really tempting when the pressure's on.
Oh, definitely been there. The firefighting mode.
Right. This is about being systematic, methodical. We can simplify it into maybe three main stages: gather symptoms, isolate the problem, and implement corrective action. But for a more robust approach, especially for complex WAN issues, we really follow a detailed seven-step process.
Okay, let's unpack those 7 steps because that firefighting approach, it's just not efficient. You can end up making things worse sometimes.
You really can. So, step one, define the problem. Sounds simple, but you need to verify a problem actually exists and then define it clearly. What exactly isn't working? Who's affected? When did it start? Get specific. Step two, gather information, identify the specific hosts, routers, switches involved, then collect data using your diagnostic toolkit. Tools like ping, traceroute, maybe telnet, or preferably slush for secure access. Then your show commands. Show interface, brief, show rip route, maybe even debug commands if you need deep insight. Think of these as your network stethoscope, its X-ray machine. Each gives you a specific piece of the health puzzle, and this directly supports that apply appropriate network troubleshooting techniques skill outcome you need for BCIS 1347.
Makes sense. Collect the evidence.
Exactly. Step three, analyze information. This is where you pull out that documentation, those baselines we talked about. You also leverage knowledge bases, maybe insights from colleagues. Put the data you gathered into context. Step four, eliminate possible causes. Be systematic. Start ruling things out based on the evidence. Like a detective eliminating suspects, you narrow it down to the most probable root cause. Step five, propose a hypothesis. Once you have a likely cause, formulate a potential solution. What do you think will fix it? Step six, test the hypothesis. Now, this is critical. Before you just make a change, assess the urgency. Always create a rollback plan. How do you undo this if it goes wrong or causes new problems? Then implement your proposed solution and crucially verify the outcome. Did it actually fix the problem? If not, you loop back. Maybe gather more info, maybe refine your hypothesis.
That rollback plan sounds vital. Don't dig yourself into a deeper hole.
Absolutely vital. Finally, step seven, solve the problem. Once the issue is resolved, don't just walk away. It's absolutely essential to document the root cause and the solution you implemented. This builds your knowledge base for the future. And this directly feeds into that develop a professional network proposal writing outcome, because good documentation is part of any professional solution. You also need to inform all the relevant stakeholders that things are back online. Following a structured approach like this saves huge amounts of time and resources, prevents further complications. It's really a critical managerial aspect for any IT department. It's the difference between chaos and efficiency.
Okay, moving on. Let's dive into something maybe a bit more complex, but absolutely fundamental to how the whole internet actually works. Border Gateway Protocol, or BGP. I often hear it called the glue of the internet. I kind of picture it like the air traffic control system for the entire internet, guiding all those millions of data packets across these vast independent networks.
That's a fantastic analogy, actually. BGP is precisely that way. It's the glue holding the internet together. It's the protocol used to exchange routing information between what we call autonomous systems, or ACs. Think of an AS as a big independent network, maybe belonging to an internet service provider, a huge corporation, a university. Each has its own internal routing policies. BGP is the system that makes sure traffic, or using your analogy, planes can fly smoothly from one AS's airspace into another's. Without BGP, the global internet reachability we all just take for granted, it simply wouldn't exist. It is complex, yes, but its importance for global connectivity just cannot be overstated. And understanding this is key to that. Identify telecommunications and data communications technology fundamentals, knowledge outcome, hashtag 2.2 common BGP troubleshooting scenarios.
That air traffic control analogy really helps visualize it. So when things go wrong in this incredibly complex global system, where do we even begin to look? Let's talk about some common BGP troubleshooting scenarios.
Right. The very first thing you almost always check is verifying BGP peering status. BGP peering is like the initial handshake between two air traffic controllers in adjacent airspaces. It's the process of establishing a TCP connection between two BGP routers so they can start exchanging routing information or flight plans. If this BGP session isn't up and running, no routes will be exchanged, period. You use the show BGP summary command. It gives you a quick status overview of all your BGP neighbors or peers. If you see a peer stuck in an idle state, that usually means BGP is trying to detect a start event, basically, trying to initiate that TCP connection or listening for the other side to initiate it.
Okay, so the connection itself isn't even forming. What causes that usually?
Well, a common issue, especially if you're peering between loopback interfaces, which are virtual interfaces often used for stability, is basic IP connectivity. You might need to run a simple ping from your loopback interface to the remote router's loopback interface to verify reachability first. Layer 3 has to work before BGP can. If the ping works, then you start checking the local BGP configuration. Are the local AS number and the remote AS number configured correctly? For instance, if you're using loopback interfaces for peering, particularly in IBGP that's interior BGP, for peers within your own autonomous system, you often absolutely need the update source loopback 0 command, assuming loopback 0 is the interface you're using. This tells the router, hey, use this loopback IP as a source address for the BGP TCP connection. Otherwise, it might try to use a physical interface as IP, and the peer might reject the connection if it's expecting the loopback IP.
Ah, subtle but critical.
Very. Similarly, for eBGP exterior BGP, peering between different ACs if the peers aren't directly connected, meaning they're not on the same subnet, you must configure the eBGP multi-hop command. See, by default, eBGP expects its peer to be just one hop away. It sets the IP packet's time to live, or TTL, to 1. If the peer is 2 or more router hops away, that packet expires before it reaches the peer, and the session fails. eBGP multi-hop tells the router to increase that TTL, allowing the BGP packets to traverse those intermediate routers. This is crucial for redundancy designs where you might peer through intermediate devices, maybe for load balancing or failover.
Okay, so we've got peering established, the controllers are talking. What's the next common hurdle? Maybe verifying missing routes, like the flight plans for certain destinations aren't showing up or aren't being shared properly.
Exactly that. That's probably the next most common category of BGP problem. Routes just aren't being advertised or received as you expect. This is obviously critical. First, let's talk about route origination. For a BGP router to advertise a network prefix, that prefix generally needs to exist in the router's routing table first, usually learned via an IGP like OSPF or EIGRP, or maybe as a static route. You can even use a static route pointing to the null 0 interface that's like a virtual black hole, specifically for advertising aggregate routes. For example, you might own a large block of addresses, but you only want to advertise the summary route, not the specifics. Pointing a static route for the summary to null 0 makes it exist in the routing table so BGP can advertise it using the network command. So if you add dprove 50.inter.50.0, it's 255.255.255.0 null 0 on router 2, then configure network 50.50.50.0 mask 255.255.255.0 under the BGP process, router 2 will start originating that 24 route into BGP.
Got it. The route has to exist locally first before BGP will share it.
Right. Then you absolutely need to understand the update exchange rules. These are fundamental BGP behaviors. When a router learns the best path to a destination from an eBGP peer, a peer in a different AS, it will generally advertise that best path to all its other peers, both its IBGP peers inside its own AS and its other eBGP peers. However, when a router learns the best path from an IBGP peer inside its own AS, it will advertise that path only to its eBGP peers. It does not re-advertise IBGP-learned routes to other IBGP peers by default. This is a crucial loop prevention mechanism known as the IBGP split horizon rule.
Ah, okay. So routes learned from inside don't get passed along to others inside?
Not automatically. This means that for all IBGP routers within your AS to learn about all the internal and external routes, they must either be fully meshed, meaning every IBGP router peers directly with every other IBGP router, which gets complex fast, or you need to use route reflectors. Route reflectors are specific IBGP routers configured to be allowed to reflect IBGP-learned routes to other IBGP clients. This avoids the need for that complex full mesh. Understanding this is essential for, configuring network connections, services, security, and management correctly.
Okay, so how do we check what's being sent and received, especially with these rules in mind?
Good question. You use specific commands. Show EPBGP neighbor XX. XX, advertised routes, shows you exactly which routes your router is sending to that specific neighbor. Show IPBGP neighbor XX, X routes, shows the routes you've received from that neighbor that has successfully passed any inbound filters you might have configured. These are the routes actually eligible to be installed in your routing table. And then there's show IPBGP neighbor XXX received routes. This one shows all routes received from that neighbor before any inbound filtering is applied. It shows you everything they sent, even the stuff you might be blocking.
That received routes one sounds super useful for debugging filters.
It is incredibly useful, but there's a catch. It requires you to configure soft reconfiguration inbound on that neighbor relationship first. What that command does is tell your router to basically keep a full, unfiltered copy of all the routes received from that neighbor stored in memory. It takes extra memory, of course, but it allows you to see everything they sent and troubleshoot your inbound filters without having to reset the BGP session.
So filters themselves can cause routes to go missing from our perspective. That sounds like a major potential pitfall for misconfiguration.
It absolutely is. BGP route filtering is extremely powerful for policy control, but it's a very common source of missing routes. You need to be careful. There are several types. Prefix filters, often using prefix lists, match and filter based on the IP prefix and mask length. AS path filters use regular expressions to match patterns in the AS path, attribute the list of AS numbers a route has traversed. Community filters match. Yes, another absolutely critical one, especially with IBGP, is the IBGP next hop behavior. When an edge router learns a route from an eBGP peer, let's say the next hop is the external peer's IP address, like 1.1.1.1. When that edge router passes the route along to its IBGP peers inside your network, by default, it leaves that next hop attribute unchanged, still 1.1.1.1. The problem is your internal routers might have no idea how to reach 1.1.1.1. That external IP address probably isn't part of your internal routing protocol like OSPF or EIGRP. So the IBGP router receives the route update, but it can't actually use the route or install it in its routing table because the next hop is unreachable. The route effectively vanishes internally.
So the internal routers don't know how to get to the external router's address. How do you fix that?
The solution is the next hop self command. You configure this on the edge router, specifically for its IBGP peering sessions. This command tells the edge router, when you advertise routes learned from eBGP peers to your IBGP peers, advertise yourself as the next hop. So the internal routers see the edge router's internal IP address as the next hop, which they do know how to reach via the internal routing protocol. Problem solved. This is such a subtle but absolutely critical design choice in datacomms, and fixing it is often a real aha moment for engineers learning BGP. Understanding these details is vital for you to be able to configure network connections, services, security, and management effectively. #T2.3 Internet reachability issues and manipulation.
Okay, so we've covered getting peers up and getting routes flowing, but it sounds like BGP is more than just basic connectivity. You mentioned influencing traffic. How does that work? It seems like it's not just about can we send traffic, but strategically controlling how we send and receive it, maybe to manage costs, improve performance, or ensure resilience against link failures.
It's exactly. Now you're thinking strategically. These are crucial managerial issues in data communications. BGP gives you levers to pull that directly affect service delivery, operational costs, and the end-user experience. Let's talk about inbound traffic manipulation first that's influencing how traffic from other networks enters your network. You don't directly control their routers, so you influence their decisions. One common technique is AS path prepending. You configure your router to add your own AS number multiple times to the AS path attribute when advertising routes to a specific peer. Since BGP routers generally prefer the paths with the shortest AS path, making your path look artificially longer encourages that peer to send traffic destined for you via a different path, perhaps through another ISP connection you have. Most network operators limit how long an AS path can be, maybe around 20 hops, to prevent abuse.
Interesting. So you make one path look less attractive to push traffic elsewhere?
Precisely. Another tool is the BGP Multi-Exit Discriminator, or MED. This is an attribute you can set on routes you advertise to a neighboring AS, usually when you have multiple connection points to that same neighbor. The neighbor AS will typically prefer the entry point associated with the lower MED value. So you can set a lower MED on your primary link and a higher MED on your backup link to influence which connection they use to send traffic to you. The default MED on Cisco iOS is typically 0. You can also use BGP communities. These are like tags you attach to routes. You can agree with your upstream provider, for example, that routes tagged with a specific community value should be given a certain local preference within their network, influencing how they route traffic towards you. But remember, a key point for Cisco iOS is that communities are not sent to eBGP peers by default. You have to explicitly enable it with the send community command on the neighbor relationship.
Okay, so that's influencing inbound. What about outbound? How do we control how our traffic leaves our network?
Outbound traffic manipulation, controlling how your traffic exits your AS towards the internet, is primarily influenced by the locale pref attribute. This attribute is only exchanged between IBGP peers within your own AS. A higher locale pref value indicates a higher degree of preference. Your routers will always prefer the path with the highest locale pre when deciding which exit point to use for a given destination prefix. So if you have multiple ISP connections, you can set a higher locale pre for routes learned via your preferred ISP, effectively forcing most of your outbound traffic to use that link. You're essentially shopping for the best internet paths for your outbound traffic, optimizing for cost or performance, much like a business optimizes its supply chain.
That's powerful control. So when you're troubleshooting general internet reachability, say, someone outside your network can't reach a server inside your network, how do you approach that, given all these influencing factors?
Troubleshooting network connectivity across the internet often becomes a distributed effort, sometimes involving coordination with other network operators. If an external network can't reach prefixes you're advertising, you start by checking your own eBGP filters on your edge routers, AS path filters, prefix lists, route maps. Are you accidentally filtering something you shouldn't be? You also need to verify that your internal IBGP propagation is working correctly. Are the routes actually reaching your edge routers from within your network? Check for issues with IBGP full mesh or route reflectors. Then you might need to work with the external AS. Are they filtering your prefixes? Perhaps based on policy or a mistake. Tools like looking glasses are invaluable here. These are web-based portals provided by many ISPs and network operators that let you run commands like ping, trace route, and check BGP routes from their perspective, looking back towards your network. It gives you crucial external visibility. Interestingly, most connectivity issues, in my experience, tend to be found closer to the network edge, often due to misconfigured filters, firewalls, or peering issues, rather than deep within the internet's transit core. Hashtag tag 2.4 BGP timers and debugging.
Okay, BGP sounds like it needs to be incredibly stable, almost like a living system that needs constant monitoring. Do these BGP connections have a kind of heartbeat to make sure they're still alive and synchronized?
That's another great analogy. BGP timers are exactly like a heartbeat monitor for those peering connections. They manage the session health and ensure routers stay synchronized. The two main timers are the keep alive timer and the hold down timer. By default, according to the BGP standard, RFC 4271, the suggested hold time is 90 seconds. Keep alive messages are then typically sent every 1/3 of the hold time, so every 30 seconds. However, many vendors, including Cisco, often default to a longer hold time, like 180 seconds, with keep alive sent every 60 seconds. If a router doesn't receive any keep alive message from its peer within the configured hold down time, it declares that peer dead, tears down the BGP session, and withdraws all the routes learned from that peer. This obviously can cause routing instability if it happens unnecessarily.
So misconfigured timers could cause sessions to flap up and down?
Absolutely. If the timers are mismatched between peers, or if network congestion causes keep alives to be delayed beyond the hold time, the session will drop. But here's a really crucial insight about BGP. It's actually designed to converge more slowly than internal protocols like OSPF or EIGRP. Stability across the vast scale of the internet is prioritized over instantaneous reaction to every little change. Understanding this deliberate slowness is key. You're not always aiming for sub-second failover with core BGP timers alone. You're aiming for stable and reliable recovery. It prevents widespread internet instability, often called route flaps.
Okay, stability over speed. Makes sense for the internet's core. But what if you need to really see what's happening inside that BGP conversation?
That's where BGP debug logs come in. When you really need to get into the weeds, the debug if BGP command family is your most powerful tool. You can enable detailed logging for specific neighbors or specific BGP update types. For example, debug IP BGP XXX updates would show you the route updates being sent to and received from neighbor XXX. But a word of caution. BGP debugs can be incredibly verbose, especially on routers with many peers and routes. They can easily overwhelm the router's CPU and fill up your console or log buffers very quickly. So it's best practice to be as specific as possible with your debug commands, maybe using access lists to filter the debug output and only turn them on for short periods while actively troubleshooting. But they provide unparalleled insight into session establishment, route exchange details, attribute processing, and any errors occurring.
That manual debugging sounds powerful but potentially overwhelming, especially in a large dynamic network. Are there specialized tools that can help manage all this BGP complexity more effectively?
Oh, absolutely. While understanding manual debugging is essential foundational knowledge, the sheer scale and complexity of BGP in large enterprises or service provider networks has definitely led to the development of specialized tools. One really good example is the Noxian Intelligent Routing Platform, often just called IRP. Platforms like this aim to simplify BGP management and troubleshooting significantly.
So it's like having an AI assistant specifically for BGP, giving you that bird's eye view and maybe flagging problems without you having to sift through endless command line output. That sounds like a huge advantage for managing things effectively.
That's a pretty good description. The IRP provides things like real-time BGP monitoring, tracking the performance of your internet paths, and generating automated alerts when problems like high latency or packet loss are detected on specific prefixes or towards certain ACs. It offers comprehensive reports and graphs showing the current state of the network, which prefixes are being actively optimized by its routing decisions, identifying problematic ACs out on the internet, and tracking how much traffic volume has been improved or shifted. This generates a detailed audit trail of ISP performance over time, which is invaluable for objectively measuring whether your providers are meeting their SLAs and for making informed, data-driven decisions about ISP selection or capacity planning. That's a significant managerial advantage.
And does it help with the actual troubleshooting too?
Yes. Platforms like IRP often integrate common troubleshooting tools directly into their interface. Things like running traceroute or ping tests from multiple points, accessing looking glass information, performing Whois lookups, or even probing specific prefixes to check reachability across different paths. It gives network administrators instant visibility into that complex middle mile of the internet, helping them quickly detect and react to interdomain routing issues or performance degradations that might be happening outside their direct control. It helps transform BGP management from a often reactive manual process into something much more proactive and data-driven. That's incredibly valuable for ensuring business continuity and optimal application performance.
Okay, great. So we've armed ourselves with documentation, a structured process like the 7 steps, and even looked at advanced BGP tools. Now let's tie it all together with a really foundational concept in networking. Troubleshooting using the layered models like OSI or TCP/IP because, like the saying goes, you can't fix what you can't find, and these models give us a kind of roadmap, right? A structure.
You've absolutely hit on a critical point there. The OSI and TCP/IP models aren't just theoretical things you memorize for an exam. They provide an incredibly powerful and, importantly, structured way to isolate network problems. When you approach troubleshooting systematically, layer by layer, you drastically reduce the guesswork and move much more efficiently towards resolving the actual problem. This directly supports learning outcomes, like identify architecture of networks to facilitate troubleshooting techniques and apply appropriate network troubleshooting techniques. The models are the architecture framework.
So we're not just randomly throwing darts at the problem, hoping to hit the bullseye. We're more like climbing a ladder, checking each rung methodically. What are some of these layered approaches people use, and when would you pick one over another?
Good question. There are several common strategies, and the best choice often depends on the symptoms you're seeing. The bottom-up approach is classic. You start at layer 1, the physical layer cables, power, interfaces, and work your way up through layer 2, data link, layer 3, network, and so on. This is excellent when you suspect a physical problem, maybe a cable unplugged or a device powered off, because you confirm the absolute foundation first. If layer 1 isn't working, nothing above it will.
Makes sense. Start at the bottom.
Then there's the top-down approach. You start at the application layer. Layer 7 is the specific application or service working, and move downwards. This can be useful for simpler problems or if you strongly suspect a software configuration issue. If the user said, I can't browse the web, you might start by checking their browser, then DNS, then work down the stack. The divide and conquer method is also very popular. You start somewhere in the middle, often at layer 3, the network layer. Can you ping the default gateway? Can you ping the destination? If your layer 3 tests work, the problem is likely higher up, layers 4 to 7. If they fail, the problem is likely lower down, layers 1 to 3. This can quickly narrow down the scope.
Okay, so you split the problem space.
Exactly. Then you have follow the path. This involves tracing the actual path traffic takes from the source to the destination, usually using tools like traceroute or traceroute on Windows. You test connectivity step by step along that path to pinpoint where the communication breaks down. Substitution is pretty straightforward. Swap out a suspected faulty component, a cable, an NIC, maybe even a whole switch with a known good one. If the problem goes away, you found your culprit. Great for suspected hardware failures. Comparison is useful too. You compare the configuration or behavior of a non-working system or component with a similar one that is working. Spotting the differences can often reveal the misconfiguration. And finally, there's the educated guess. This is less systematic, obviously, but it relies on your experience. Based on the symptoms, you might have a strong hunch about the likely cause and jump straight to testing that hypothesis. It gets faster with experience, but it's risky if you guess wrong. The real insight here, though, is that an experienced troubleshooter develops an intuition for which method to apply first based on the initial symptoms and their understanding of how networks behave.
3.2 symptoms and causes at each layer.
That makes perfect sense. Different tools for different situations. Now let's maybe break down the typical symptoms and common causes you might see at each layer. This feels like a really useful mental checklist to run through when a problem first pops up.
It absolutely is. Understanding these common correlations helps you quickly narrow down possibilities. And knowing this stuff also helps you satisfy those learning outcomes about explaining transmission media and identifying cables and connectors, because layer 1 is all about that physical stuff. So, starting at the bottom, the physical layer, layer 1. Symptoms here might include network performance suddenly dropping way below your established baseline, maybe a complete loss of connectivity for a device or segment, network bottlenecks or congestion appearing, maybe high CPU utilization on connected devices trying to handle errors, or specific console error messages pointing to interface hardware issues. Common causes. Power issues seriously. Always check if it's plugged in and powered on. Hardware faults, a bad network interface card, an IC, a faulty switch port, maybe even just an outdated NIC driver. Cabling faults are huge. Damaged cables using the wrong type of cable, like Cat5 in a gigabit network. Poorly crimped connectors, cables that are too long causing signal degradation, attenuation, or loose connections. Also, noise from electromagnetic interference, EMI. Maybe a cable run too close to fluorescent lights or heavy machinery. Interface configuration errors are common too, like incorrect clock rates on older serial WAN links, or simply forgetting the no shutdown command on a Cisco interface. And sometimes devices are just overloaded, exceeding their design limits for traffic or processing, leading to high CPU, drop packets in interface queues, check show interface for input-output queue drops, or SNMP management timeouts because the device is too busy to respond.
Wow, okay. A lot can go wrong just at layer 1. What about layer 2?
Moving up to the data lake layer, layer 2. Symptoms here could be things like no network layer 3 functionality at all, even if layer 1 seems okay. Performance might be operating below baseline because layer 2 isn't finding the optimal path. Maybe STP issues. You might see excessive broadcasts flooding the network, a broadcast storm, which can bring everything grinding to a halt. Or you might see those infamous line protocol down console messages on an interface, even when the physical interface itself shows as up. What causes these? Often encapsulation errors. Maybe one end of a WAN link is configured for PPP encapsulation and the other end is expecting HDLC. They can't talk. Address mapping errors like problems with RRP, address resolution protocol, where a device can't map an IP address to the correct MGASI address, preventing communication on the local segment. Framing errors, often caused by noisy lines, or very commonly, duplex mismatches. That's where one side of a link is set to full duplex and the other is set to half duplex. This causes massive collisions and errors, and especially in switched networks. Spanning tree protocol, STP failures can cause forwarding loops, leading to broadcast storms, or malfunctioning STP might incorrectly block ports, causing connectivity loss or excessive traffic flooding.
Duplex mismatches. Hear about those a lot. Okay, layer 3.
At the network layer, layer 3, the domain of IP addressing and routing. Symptoms here tend to be broader, maybe general network failure affecting all users, or perhaps suboptimal performance affecting only a subset of users or applications trying to reach certain destinations. Common causes often stem from recent general network changes. Someone reconfigured a router, added a new network segment. Underlying connectivity issues at layer 1 or 2 that weren't fully resolved can manifest as layer 3 problems. Big ones are routing table issues, missing routes destinations, incorrect routes, maybe suboptimal routes being preferred. Neighbor issues are frequent too, meaning routing protocol adjacencies like OSPF or EIGRP neighbors failing to form or dropping, which prevents routes from being exchanged correctly. Or sometimes there are problems within a routing protocol's internal topology database, like inconsistencies in OSPF's link state database, LSDB. This is where understanding network architecture really becomes crucial for effective troubleshooting.
Right, the routing logic itself breaks down. What about layer 4?
The transport layer, layer 4, TCP, and UDP land. Problems here usually manifest as issues with specific application connectivity, while other applications might work fine. The number one culprit here, access control list, ACL, misconfigurations. So many ways ACLs can go wrong. Incorrect logic blocking needed traffic flow. The order of entries matters hugely. ACLs are processed top-down, first match wins. Forgetting the implicit deny any at the end of every ACL which blocks anything not explicitly permitted, using incorrect wildcard masks, selecting the wrong protocol, TCP versus UDP versus ICMP, or port numbers, or misusing the established keyword which is meant to allow return traffic for TCP sessions. Also, network address translation, NAT interoperability, can cause headaches at layer 4, especially for certain protocols that embed IP addresses within their data payload, or for protocols like BOT-PDHCP, DNS, SNMP, or specific tunneling and encryption protocols that might not traverse NAT gateway smoothly without specific configurations or helpers. This layer is really critical when you're configuring network connections, services, security, and management policies.
ACLs and NAT. Got it. Sounds like fertile ground for errors. And finally, layer 7.
Finally, the application layer, layer 7, where the user actually interacts with network services. Symptoms here are usually pretty straightforward. Specific network resources are unreachable or unusable. Users can't SSH or telnet to a server. Websites, HTTP, TTPS won't load. File transfers, FTP, TFTP fail. Email, SMTP, PPO isn't working. Network management queries, SNMP, timeout, name resolution, DNS fails, or network file shares, NFS, are inaccessible. The causes here can be misconfigured application services themselves on the server. Maybe a web server isn't running, or a firewall on the server is blocking the port. It could also be firewall blocks elsewhere in the network path, specifically targeting that application port. But quite often, a layer 7 problem is actually just a symptom of an underlying issue at one of the lower layers, 1 through 4, that's preventing the application traffic from getting through in the first place. The real insight. Don't just assume a layer 7 failure is a layer 7 problem. Often the root cause lies beneath. #tag4 practical IP connectivity troubleshooting steps.
Okay, that layer-by-layer breakdown is incredibly helpful for mentally organizing where a problem might be. Now let's get really practical. Let's walk through some step-by-step troubleshooting for basic IP connectivity. This is where we put that theory into action, right? Especially when we face those really frustrating ping or traceroute failures that just tell us, nope, can't get there, but don't say why.
Precisely. This section directly hits those learning outcomes about designing logical and physical networks, configuring connections and security, and of course, applying troubleshooting techniques. We'll use a structured, mostly bottom-up approach here to systematically tackle those end-to-end IP connectivity problems. Step 1. Verify the physical layer. Always start here. Use the Show Interfaces command on your Cisco router or switch. What are you looking for? Ideally, interface is up, line protocol is up, but dig deeper. Look at the counters. Are there high numbers of input or output errors, CRC errors, runts, giants, input or output queue drops? These counters can be gold mines, pointing towards bad cables, failing hardware, speed duplex issues, or maybe just a link being completely overwhelmed with traffic.
Okay, check the interface status and error counters. What's next?
Step 2. Check for duplex mismatches. We mentioned this as a layer 2 cause, but it's worth specifically checking, especially on fast Ethernet links where auto-negotiation wasn't always perfect, or if someone manually configured speeds in duplex settings. Gigabit Ethernet pretty much requires auto-negotiation, but a manual misconfiguration can still happen. One side set to full duplex, the other hard-coded to half duplex. That's a recipe for massive collisions, errors, terrible performance. Use that Show Interface Name command again. Look for the line showing the speed and duplex settings. If you suspect a mismatch, try setting both sides to duplex auto and speed auto, or explicitly configure them to match. Jebel duplex full, speed 100 on both ends.
Got it. Duplex mismatch, bad news. Step 3.
Step 3. Verify addressing on the local network. This covers both layer 2 MC addresses and layer 3 IP addresses on the local segment. On a Windows PC, use ARPieto. This shows the ARP cache the mapping between IP addresses and M addresses the PC knows about on its local network. Is the default gateway's IP address mapped to the correct MXC address? On a Cisco switch, use Show MAC Address Table. This tells you which MAC addresses the switch has learned, which port it learned them on, and crucially, which VLAN they belong to. A very common issue, especially in environments with multiple VLANs, is a simple VLAN assignment mistake. A user's PC is plugged into a switch port that's configured for the wrong VLAN, so it can't talk to its default gateway or other devices in its intended subnet. checking the ACA table against the port's configuration, sure run interface name, and correcting the VLAN assignment, example switchport access VLAN 10, often fixes things. This directly relates back to identifying infrastructure, cables, connectors, and VLAN configurations.
The dreaded wrong VLAN assignment. Seen that one before. Okay, step 4.
Step 4. Verify the default gateway. This is probably one of the most common reasons why a device can talk to things on its own local subnet, but can't reach anything outside of it. The device simply doesn't know where to send traffic destined for other networks. On the end device, like a PC, check its IP configuration. Does it have a default gateway configured? Is it the correct IP address for the router interface serving its subnet? Use ipconfig, all Windows, or ipedder-show, iproot-show, Linux. On the router itself, use show iproute to check its routing table. Does it have routes to other networks? Does it have a default route, gateway of last resort, configured if it needs to reach the internet? Use show ipinterface brief to confirm the IP address configured on the interface that should be the default gateway for the clients. And think about IPv6 too. A PC might fail to get its IPv6 address via SLAA, stateless address auto configuration, if the local router isn't correctly configured for IPv6 routing. A common fix is simply enabling IPv6 routing globally on the router with IPv6 unicast routing. This command makes the router join the necessary multicast groups, like FS0 2.2 all IPv6 routers, so SLA key can actually work.
Good point about IPv6. Easy to overlook. Step 5.
Step 5. Verify the correct path. Assuming basic connectivity and routing seem okay, maybe traffic is just taking an unexpected or incorrect path. Remember that routers make forwarding decisions based on the longest prefix match in their routing table. They look for the entry that matches the destination IP address using the greatest number of leftmost bits. Use the traceroute or tracert command from the source device towards the destination. This tool sends packets with incrementally increasing TTL values to map out the sequence of router hops the traffic is taking. Does the path shown by traceroute match what you expect based on your network design and routing tables? If not, you need to investigate why routing is sending traffic down the wrong road.
Traceroute essential for path discovery. Okay, step 6. Step 6. Verify the transport layer. Now we're thinking about layers 3 and 4, specifically potential blocking by firewalls or NAT issues. The Telnet utility can be surprisingly useful here, even if you don't actually use Telnet for management anymore. You can use it to test connectivity to a specific TCP port on a remote device. For example, try Telnet server IP address 80 to test connectivity to a web server's port 80, or Telnet server IP address 22 for SSH. If the connection immediately fails, connection refused, or times out, it strongly suggests something is blocking that specific port, likely an ACL or a firewall rule somewhere along the path, or perhaps the service isn't even running on the server. If the screen goes blank or you get some banner text, it means you've successfully established a TCP session at layer 4, and the problem likely isn't basic firewall blocking, though application-level issues could still exist.
Clever use of Telnet for port checking. Step 7.
Step 7. Verify ACLs. We just mentioned them, but let's focus specifically. Access control lists are a huge source of "why can't I get there?" problems. Check ACLs applied to router interfaces along the path using show IP interface name, include access lists or show access lists. Remember, ACLs can block traffic in either the inbound or outbound direction. A very common mistake is applying an ACL to the wrong interface or in the wrong direction, in versus out. For example, maybe ACL 100 was intended to filter traffic leaving the network via the serial 011 interface, but someone accidentally applied it inbound on the internal Gigabit Ethernet 1000 row interface, blocking legitimate internal traffic. Carefully review the ACL logic and where it's applied. Correcting the interface or direction often resolves the issue. This is core to configuring network security and management.
Right. Check the logic AND, the application point. Good tip. Last step.
Finally, step 8. Verify DNS. If users are complaining they can't reach www.google.com, but they can ping Google's IP address like 8.8.8.8, the problem is almost certainly DNS domain name system. DNS is what translates human-friendly names into machine-usable IP addresses. Check the DNS server settings on the client device, ipconfig all. Can the client ping its configured DNS server? On a Windows PC, use the nslookup command to test name resolution directly. Try nslookup www.google.com. Does it return the correct IP address? If not, try nslookup www.google.com 8.8 to specifically query Google's public DNS server. This helps isolate if the problem is the local DNS server or broader connectivity. On a Cisco router, you can configure DNS servers, so you name our server shift, and test using the ping www.google.com command, or create static mappings for testing with a map host hostname IP address. Following these 8 steps systematically, usually starting from the bottom up, help you diagnose and resolve the vast majority of basic IP connectivity issues you'll encounter.
And mastering this process is key to effectively designing, developing, configuring, and troubleshooting networks, skills essential for your coursework and those industry certification exams.
That practical troubleshooting walkthrough was incredibly helpful, really breaks it down. Now, let's maybe pivot a bit. Let's move from fixing problems reactively to making strategic design decisions that might prevent them or at least make the network behave predictably in the first place. Choosing the right routing protocol, whether it's an interior gateway protocol, IGP, like EIGRP or OSPF, or using BGP internally, isn't just some technical detail only network engineers care about, is it? It sounds like a critical strategic choice for any network design, impacting the organization's future.
You are absolutely right. It's far more than just a technical implementation detail. The choice of routing protocol profoundly impacts a network's performance, its scalability, its resilience, and its flexibility to adapt to future needs. This decision is absolutely central to the BCIS 1347 course's focus on design, integration, selection, and implementation of communication solutions. Making informed choices here is also crucial preparation for those industry-standard network certification exams like Network Plus, JOC, because they test your understanding of these fundamental trade-offs. #5.1 EIGRP, Enhanced Interior Gateway Routing Protocol.
Okay, let's start with one of the common ones, especially in Cisco shops. EIGRP. I heard a funny analogy for EIGRP once. EIGRP is like your dad great at his job, maybe, but only likes one brand of car. What are the real pros and cons here, especially thinking from a business strategy angle?
That analogy captures its main limitation perfectly. Let's break it down. The pros of EIGRP are significant, especially historically. It's generally considered very easy to configure and deploy, particularly in an all-Cisco environment. Its core algorithm, DUIL, diffusing update algorithm, provides incredibly fast convergence times when a network change occurs like a link failing. That's a huge plus for minimizing downtime. EIGRP also offers very flexible route summarization. You can summarize routes pretty much anywhere in the network hierarchy, which helps control the size of routing tables and limit the scope of routing updates. This makes it particularly well suited for simpler hub-and-spoke network topologies, which are common in many traditional enterprise WANs.
Fast convergence, easy setup in Cisco world. Sounds good. What's the catch? The one brand of car part.
Exactly. The biggest con is that proprietary nature. While Cisco did release some basic EIGRP specifications as an informational RFC back in 2013, calling it Open EIGRP, the core DUIL algorithm, the secret sauce that gives it that speed advantage, remains proprietary Cisco technology. This creates vendor lock-in. From a business perspective, this limits your flexibility. What if you want to introduce network equipment from another vendor? A firewall, a load balancer, maybe switches from Juniper or Arista. You can't run EIGRP on them. This forces you into complex and often fragile route redistribution setups where you're translating routes between EIGRP and another protocol like OSPF or BGP. Redistribution can get messy, introduce routing loops if not done carefully with route tagging and filtering, and it adds significant operational complexity. Furthermore, even within the Cisco ecosystem, support hasn't always been universal or immediate for newer platforms. For instance, it took a while for Cisco's ACI, application-centric infrastructure data center solution, to fully support EIGRP, and multi-site ACI still has limitations. So a heavy reliance on EIGRP can sometimes hinder your ability to adopt newer, potentially multi-vendor technologies, potentially slowing down innovation or forcing more expensive single-vendor solutions. That strategic limitation is a big deal. #5.2 OSPF, open shortest path first.
That vendor lock-in and redistribution complexity definitely sounds like a strategic headache. So in contrast, let's talk about OSPF. The analogy I heard for OSPF was, OSPF is like your mom. It cleans up after you and makes sure you can't hurt yourself too badly. That sounds much more open and maybe forgiving for network design.
It is, in many important ways. The biggest pro of OSPF, without question, is that it's an open standard. It's defined by IETF RFCs, and pretty much every network vendor under the sun supports it. This immediately eliminates that vendor lock-in problem EIGRP presents. It gives businesses much more choice in hardware selection, potentially leading to better pricing through competitive bidding. It fosters interoperability. OSPF is also generally pretty straightforward to configure for basic setups, especially in small to medium-sized networks. And it's inherently well-suited for mesh topology, where you have multiple paths between nodes, which is increasingly common in modern, highly available data center designs. OSPF is also very flexible when it comes to integrating with more advanced technologies like MPLS, multi-protocol label switching, VRFs, virtual routing and forwarding, used for network segmentation, and various Layer 3 and Layer 2 VPN services. This makes it highly adaptable for complex service provider or large enterprise networks.
Open standard, multi-vendor, good for mesh. Sounds like a strong contender. What are the downsides then? Why isn't it always the default choice?
Well, OSPF does have its cons, or perhaps design considerations. It has a more rigid hierarchical structure based on areas. While areas help control routing updates and limit the scope of calculations, route summarization in OSPF can only occur at the boundaries between areas, specifically on area border routers, ABRs. You can't just summarize anywhere you like, as you can with EIGRP. This means OSPF demands more careful area design and IP addressing planning up front. If your IP addressing scheme isn't contiguous or well-structured, effective summarization can be difficult or impossible, leading to larger routing tables. Also, because it's a link state protocol, certain types of route changes, like a link flapping, can trigger SPF, shortest path first, algorithm recalculations across an entire area, which can consume significant CPU cycles on routers, potentially delaying conversions or causing instability in poorly designed networks. And compared to BGP, OSPF offers less flexibility for granular traffic influence. You primarily influence path selection by adjusting interface costs. While effective, it's less nuanced than the rich set of policy attributes available in BGP. So while OSPF offers openness and robustness, it demands more rigorous planning and design discipline compared to the initial simplicity of EIGRP in some scenarios. Hashtag 5.3 BGP, Border Gateway Protocol, as an IGP.
Okay, EIGRP is fast, but potentially locks you in. OSPF is open, but needs careful design. Then there's the big one we talked about earlier, BGP, the Internet's coordinator. The analogy there was maybe your uncle that hands you a rope and a gun and tells you to go have fun. Sounds powerful, flexible, but maybe a bit dangerous if you're not careful. Can you actually use BGP inside your own network as an interior gateway protocol instead of just at the edge? And what are the strategic implications of doing that?
That analogy really does capture the spirit of using BGP internally. Yes, you absolutely can use BGP as an IGP, and it's actually becoming increasingly common in specific use cases, especially in very large data centers for building scalable IP fabric underlays, or for connecting enterprise networks directly to cloud providers like Azure and AWS, who often prefer or require BGP peering. The pros of using BGP internally are significant, particularly around control and scale. It is incredibly powerful and offers unparalleled flexibility for traffic engineering. You get fine-grained, per-prefix control over how traffic flows using a whole toolbox of attributes. Local pref, the origin attribute, MD, communities, S-path prepending, the list goes on. This level of control is far more nuanced than just tweaking OSPF interface cost. It allows you to implement sophisticated policy-based routing to meet specific business requirements around cost, performance, latency, or resilience. BGP is also excellent for route recognition and troubleshooting in complex environments. With a simple show IPRA BGP, you can often instantly see which AS or which specific router originated a particular subnet prefix thanks to the ACE path attribute. That's invaluable in large distributed networks. And for connecting multiple sites together, especially if each site is assigned its own private AS number, from the private ACE range 64512-65534, using IBGP between sites can actually be quite simple conceptually and scales very well. It's also essentially required if you have multi-homed connections to different ISPs and want to influence both your inbound and outbound internet traffic paths effectively.
Okay, that sounds compelling, especially the traffic engineering part. But that rope and gun analogy implies danger. What are the downsides or complexities?
Right, the cons are definitely important to weigh. As we discussed earlier, BGP is innately slower to converge than IGPs like EIGRP or OSPF. That's by design, prioritizing internet-wide stability. While technologies like BFD, bidirectional forwarding detection, can provide very fast detection of direct link or peer failures between adjacent routers, allowing for quicker rerouting around that specific failure. BFD doesn't fundamentally change the slower propagation speed of BGP route advertisements or withdrawals across the wider network. It takes time for BGP updates to ripper through. Also, BGP typically still needs an underlying IGP, like OSPF or even static routes, running within your network. Why? To provide the basic IP reachability between the BGP routers themselves, especially if they're not directly connected, BGP needs to establish TCP sessions, and TCP needs underlying IP connectivity. And as we touched on, IBGP has that split horizon rule. To ensure all IBGP routers learn all the routes, you either need that potentially complex full mesh of IBGP sessions, or you need to carefully design and configure route reflectors or confederations. This adds significant configuration overhead and potential points of failure compared to the simpler neighbor discovery no OSPF or EIGRP. So while BGP offers immense power and granular control, it absolutely comes with a steeper learning curve and more complex design considerations. It's like being handed a very sophisticated tool. It can build amazing things, but it demands real expertise to wield safely and effectively. Tag 5.4 hybrid approaches and strategic considerations.
That's a really clear picture of the trade-offs for each. It definitely sounds like there's no single best routing protocol for every situation. It's much more about finding the best fit for the specific needs and constraints of a given network environment. So, how do businesses typically navigate these choices in the real world? Do they usually just pick one and stick with it, or do they mix and match? What's a common strategy?
Exactly. It's rarely a one-size-fits-all decision. It's about picking the right tool, or often the right combination of tools for the job. Given the pros and cons we've just discussed, a very common and often highly effective strategy is to use hybrid approaches. Probably the most prevalent hybrid model you'll see in medium to large enterprises is using an IGP like OSPF for internal routing within each site, campus, or data center LAN. OSPF handles the local routing quickly and efficiently. And then they use BGP for the connections between sites across the wide area network or for connecting out to service providers and the internet. This approach lets you leverage the strengths of both: the speed, simplicity, and fast convergence of OSPF for the internal networks where vendor interop might be less critical, combined with the scalability, stability, and powerful policy control of BGP for the more complex intersite and external connections where traffic engineering and multi-vendor peering are essential. It's often the best of both worlds.
That hybrid OSPF BGP model makes a lot of sense. Balance speed inside with control outside.
It really does. So when making these decisions, the key decision drivers usually boil down to a few things. Concerns about vendor lock-in. If avoiding dependency on a single vendor is a high priority, open standards like OSPF and BGP are strongly favored over EIGRP. Network size and expected growth. Are you managing less than 50 routers or hundreds or thousands? The scaling characteristics and complexity management differ significantly between protocols. The network topology is primarily a simple hub-and-spoke WAN or a complex mesh data center fabric. EIGRP might be simpler for basic hub-and-spoke, while OSPF or BGP handle mesh better. Summarization needs. How important is flexible route summarization? EIGRP and BGP generally offer more flexibility here than OSPF's stricter area-based summarization. And critically, your traffic engineering requirements. If you need granular control over routing paths to manage costs, enforce QoS policies, ensure resilience over multiple paths, or connect to multiple ISPs effectively, BGP is almost always the superior choice, often justifying its added complexity.
Okay, that's a great checklist of factors.
And one last point here is worth briefly mentioning SD-WAN, software-defined wide area network, again in this context. SD-WAN represents a modern evolution in how WANs are managed and how routing decisions are made. Often, SD-WAN solutions use standard protocols like BGP or OSPF underneath the covers to establish connectivity, but they add an intelligent overlay and a centralized controller that abstracts much of the underlying complexity. This controller makes dynamic, policy-based routing decisions across multiple transport links, MPLS, Internet, LTE, based on real-time application performance needs. So SD-WAN is becoming a very important alternative or complement to traditional routing protocol choices, especially for managing complex distributed WANs connecting to cloud services. Understanding all these options, EAUVP, OSPF, BGP, hybrid models, and SD-WAN, is crucial for you to be able to select appropriate wired, wireless, and optical networking components and to grasp the current and future impact of these technologies on business strategy and IT operations.
All right, as our networks keep expanding, connecting more users, more sites, more clouds, secure data communications and having really robust security strategies aren't just, nice to haves anymore. They're absolutely paramount. Data security is a board level concern these days. So let's dig into how modern WAN solutions, specifically VPNs and SD-WAN, are tackling these critical security challenges.
This is a hugely important area, and it directly integrates with your course's focus on selecting communication solutions, handling design integration, selection, and implementation, and particularly helps you practice formulating risk assessments and developing appropriate security strategies to mitigate those risks. The core insight here, really, is that security can no longer be bolted on as an afterthought. It absolutely must be designed into the very fabric of your network infrastructure from day one. It's foundational.
Okay, let's start with a technology most people have probably heard of, maybe even used personally, virtual private networks or VPNs. What are they really, beyond just masking your IP address for streaming? How do they fit into the modern WAN security picture, especially for businesses?
Right. At its core, a VPN is essentially an encrypted connection, a secure tunnel that protects data transmission between devices when it travels over a public network like the internet. Think of it like building your own secure, private, armored tunnel through the middle of the public highway system. Only authorized vehicles, your data packets, with the right keys can get in and travel through it securely. Hashtag tag 6.1.1 types and uses. Now, while the core tech is similar, there are two main categories with distinct purposes: business VPNs and personal VPNs. Business VPNs are primarily designed for two things. First, secure remote access, allowing employees working from home, traveling, wherever, to connect securely back to the corporate network and access internal resources like file servers or applications as if they were sitting in the office. Second, secure site-to-site connectivity, creating permanent encrypted tunnels between branch offices and headquarters, for example, linking their networks together securely over the internet instead of relying on extensive private lines. The priorities for business VPNs are controlled access based on user identity and role, strong security for sensitive corporate data, and ensuring predictable performance for business-critical applications running over the VPN.
Okay, secure corporate access. What about personal VPNs?
Personal VPNs are geared towards individuals seeking primarily privacy, security on untrusted networks like public Wi-Fi, and potentially unrestricted internet access. They work by masking your real IP address, making it harder for websites and advertisers to track you online. They encrypt all your internet traffic, protecting it from eavesdroppers, especially on open Wi-Fi hotspots in coffee shops or airports where your data would otherwise be easily intercepted. People also use personal VPNs to bypass geographic restrictions on content, like streaming services, or to circumvent censorship in certain countries. Essentially, it helps anonymize your online activity and secure your connection. Hashtag tag 6 on 1.2, how they work.
So how do these secure tunnels actually get created and function? What's happening under the hood when I click connect on my VPN app?
Okay, let's break that down. For a business VPN, when an employee initiates a connection using VPN client software on their laptop or phone, that software establishes a secure, authenticated connection to a VPN gateway device or server managed by their organization. This gateway usually sits at the edge of the corporate network, maybe in the HQ data center. Once authenticated, proving who they are, all the network traffic from that employee's device designated for the corporate network is encrypted and sent through this secure tunnel to the gateway. The gateway decrypts it and forwards it to the internal resources. Traffic coming back follows the reverse path. It makes the remote user appear, from the network's perspective, as if they are logically inside the company's private network. The VPN system continuously verifies the user's identity and enforces IT-defined access policies based on their role.
Okay, encrypted tunnel into the corporate network. How does the personal VPN differ?
For a personal VPN, the process is similar but simpler from the user's end, and the destination is different. The user typically installs an app from the VPN provider, maybe selects a server location, like connect me to a server in Switzerland, and hits connect. The app then encrypts all or selected internet traffic leaving the user's device. This encrypted traffic is sent through a secure tunnel to the VPN provider's remote server in the chosen location, Switzerland in our example. That VPN server decrypts the traffic, then sends it out onto the public internet towards its final destination, like the website you're visiting. Crucially, the traffic now appears to originate from the VPN server's IP address in Switzerland, not the user's real IP address at home or the coffee shop. This masks the user's true location and identity. The return traffic comes back to the VPN server, gets encrypted again, and is sent back through the tunnel to the user's device. Hashtag tag 6.1.3 key features and benefits.
Got it. So the core benefit for both is definitely that encrypted tunnel securing data in transit.
Oh.
But what are some of the more specific features that differentiate them beyond just who manages the endpoint?
Yeah, while both share that fundamental benefit of securing data in transit, and VPNs are a very mature, durable technology, their specific feature sets definitely diverge based on their target users. For business VPNs, key features often include robust authentication and access control. They need to integrate with corporate identity systems, supporting methods like Kerberos, Radius, LDAP, maybe modern standards like SAML 2.0 for single sign-on, and almost always multi-factor authentication, MFA for stronger security. They often perform host or endpoint health checks, verifying that the connecting device meets certain security requirements, like having up-to-date antivirus and patches, before allowing it onto the network. This is sometimes called posture assessment. They offer flexibility, maybe allowing for always-on VPN connections that establish automatically, but perhaps with split tunneling exceptions where non-critical traffic, like streaming music, can go directly to the internet to reduce load on the corporate gateway. And increasingly, they utilize cloud-based gateways for better scalability and performance, making it easier to handle large numbers of remote users without bottlenecking at a single physical appliance.
Okay, strong auth, endpoint checks, scalability. What about personal VPN features?
Personal VPNs tend to focus more on individual privacy and usability features. Core features include IP address masking, hiding your real IP, strong data encryption, usually AES-256 nowadays, and often a kill switch. A kill switch is important. It automatically blocks all internet traffic from your device if the VPN connection unexpectedly drops, preventing your real IP or unencrypted data from being exposed accidentally. Many also offer two-factor authentication just to log into the VPN service account itself. Split tunneling is common here too, letting you choose which apps use the VPN and which don't. Example, route your browser through the VPN, but let your online game connect directly for lower latency. Auto-connect features ensure the VPN activates automatically on certain networks like untrusted Wi-Fi. More advanced features might include obfuscated servers, which try to disguise VPN traffic to look like regular HTTPS traffic, making it harder for networks or governments to detect and block VPN use. Double VPN or multi-hop routes your traffic through two different VPN servers for an extra layer of obfuscation. Some integrate with Onion over VPN for routing traffic through the Tor network after the VPN connection for maximum anonymity. And increasingly, many offer threat protection features that block ads, trackers, or known malicious websites at the VPN level. Hashtag 6.1.4 security limitations.
Wow, some of those personal VPN features sound pretty advanced for privacy. But going back to the core security, you mentioned VPNs secure the tunnel. Are they a complete security solution on their own, or are there still blind spots we need to be aware of?
That's a really critical question to ask, and the answer is a definite no. While VPNs are generally very safe and effective for securing data in transit over the internet, they're absolutely not a 100% foolproof security solution on their own, and they certainly don't constitute a complete network security strategy for any organization or individual. For businesses, traditional VPNs primarily secure that tunnel between the remote endpoint and the corporate gateway. They don't inherently protect the endpoint device itself from malware infection. If a remote user's laptop gets compromised with ransomware, the VPN provides a nice secure tunnel for that ransomware to potentially spread into the corporate network. VPNs don't typically inspect the traffic content for threats unless integrated with other security services. They also don't stop phishing attacks or protect against threats after a device or account is already compromised.
That's why business VPNs absolutely need to be paired with broader network security platforms. Things like endpoint detection and response, EDR, on laptops, strong firewalls at the gateway, intrusion detection systems, maybe zero trust network access, ZTNA concepts, which continuously verify trust instead of just relying on the initial VPN connection.
Okay, so secure tunnel, but not necessarily secure endpoints or content inspection. What about personal VPN limitations?
Similar limitations apply to personal VPNs. They encrypt your connection and mask your IP, which is great for privacy and security on public Wi-Fi. But they won't magically block malware if you download a malicious file or stop you from entering your credentials on a convincing phishing website. They also don't necessarily protect you from tracking methods that don't rely solely on your IP address, like browser fingerprinting or cookies, though some VPNs bundle tracker blocking. And the level of trust you place in the VPN provider itself is crucial. Are they truly keeping no logs of your activity as they claim? So for both business and personal use, the key takeaway is that VPNs are a powerful tool for securing connections, but they must be complemented by other security layers. Good endpoint security, antivirus, anti-malware, strong passwords, and MFA everywhere, user awareness training, especially against phishing, robust firewalls, and maybe more advanced network security monitoring tools for businesses. The true insight is always, security requires a layered defense and depth strategy. VPN is just one important layer.
That makes perfect sense, security in layers, not just one tool. This leads us naturally to the other major modern WAN technology, SD-WAN, or Software-Defined Wide Area Network. How does SD-WAN compare to the VPNs we just discussed? Is it just a fancier, more automated VPN, or is it something fundamentally different that business students really need to understand?
It's definitely more than just a fancier VPN. It represents a fundamentally different approach to building and managing wide area networks, although it often utilizes VPN technologies like IPsec tunnels underneath as part of its secure overlay. While a traditional VPN typically creates a single, relatively static encrypted tunnel between 2 points, like a remote user in HQ or two branch offices, SD-WAN takes a broader, more flexible, and application-aware, intelligent approach to connecting locations and users. It essentially decouples the network control plane, the brains, from the data plane, the pipes. It uses a centralized controller to manage the entire WAN fabric, allowing you to define policies based on business needs and application requirements. The key difference is its ability to dynamically route traffic across multiple connection types simultaneously. Maybe you have an expensive MPLS link, a cheaper broadband internet connection, and maybe even a 4G 5G LTE connection at a branch site. SD-WAN can intelligently steer traffic for, say, critical real-time voice calls over the low-latency MPLS link while sending less critical bulk data transfers over the cheaper broadband link, and maybe using LTE as a backup or for extra capacity. This steering is done based on real-time network conditions, latency, jitter, packet loss on each link, the type of application traffic identified, using deep packet inspection, or specific business policies you define. Salesforce traffic always prefers the MPLS link. This results in much greater flexibility, potentially better performance and reliability for critical applications, often lower cost by leveraging cheaper internet bandwidth, and significantly simplified centralized management and control across potentially hundreds or thousands of distributed sites.
Okay, so it's like an intelligent traffic cop for your entire WAN, using multiple roads and routing cars applications based on their importance and real-time route conditions.
That's a great analogy. A traditional VPN is like having just one secure road, maybe a toll road, MPLS. SD-WAN is like having that toll road, plus a regular highway broadband, plus maybe some local routes, LTE, and an intelligent traffic management system, the SD-WAN controller, constantly watching traffic and road conditions, dynamically telling each car which road to take to get the best performance based on your rules. This directly addresses those course outcomes about selecting appropriate wired, wireless, and optical networking components, and identifying diverse broadband access solutions like cellular SD-WAN is designed to leverage all of them intelligently. It abstracts much of the underlying network complexity, offering a much more sophisticated orchestration of your WAN resources compared to traditional static VPN tunnels. Hashtag 6.2.2 SD-WAN security best practices.
That dynamic, policy-driven routing sounds like it offers huge advantages for performance, agility, maybe even cost savings. But what about the security side of SD-WAN? Does all that intelligence and dynamic behavior introduce new security challenges or considerations?
It absolutely does. But SD-WAN platforms are also designed with security as a core component, often integrating many security functions directly. However, just like any complex system, implementing SD-WAN securely requires adhering to robust best practices. This is crucial for formulating that risk assessment and developing an appropriate security strategy. First, think about foundational security. Don't forget the basics. SD-WAN branches can and should leverage existing network infrastructure services like DNS, DHCP, and IP address management, ITAM, for security. Secure DNS, for example, can be a powerful first line of defense, blocking connections to known malicious domains. Monitoring DNS queries can also provide early warnings for command and control traffic from potentially compromised devices inside your network trying to phone home. Second, pay critical attention to default settings. Never, ever assume the vendor's default configuration is secure for your environment. Vendors often leave certain ports or protocols open by default for ease of initial setup or compatibility, creating an unnecessary attack surface. You must review and customize all default security settings, hardening the configuration according to your policies.
Right. Don't trust the defaults.
Never. Third, access control and management plane security is paramount. The SD-WAN controller and management interfaces are high-value targets. Restrict physical access to SD-WAN hardware. Limit administrative logins, SSH, HTTPS, to only authorized management IP addresses or dedicated isolated management networks. Always enforce strong passwords and multi-factor authentication, MFA, for all administrative access. Ensure management sessions are encrypted, and meticulously log all administrative access and configuration changes for auditing and incident response. Fourth, onboarding security for new SD-WAN appliances joining the fabric needs to be strict. The principle should be default state, not allowed. New devices shouldn't automatically be trusted or allowed onto the network. Require positive identification and authorization, maybe via a unique serial number registered with the controller, importing a device-specific license or token, or using certificate-based authentication before the device is admitted to the SD-WAN fabric. Automated network discovery tools can also help detect unauthorized or rogue devices attempting to connect.
Okay, secure the management, secure the onboarding. What about the actual data traffic?
Fifth, data plane security. The overlay network that carries the actual user traffic between SD-WAN sites must be encrypted. This is typically done using standard protocols like IPsec or sometimes proprietary variations of SSL/TLS, creating secure tunnels over the underlying transport links, Internet, MPLS, etc. Use strong encryption algorithms like AES-128 or preferably AES-256 with robust authentication and ensure frequent automated key rotation. Ideally, use unique encryption keys for each tunnel or appliance pair. Sixth, think about perimeter security. Many SD-WAN solutions now integrate firewall capabilities directly into the branch appliance, providing distributed perimeter security. This allows for continuous cyber surveillance and enforcement of security policies right at the branch edge, closer to the users and devices. Use these capabilities for things like microsegmentation, creating policies to isolate different types of traffic. For example, guest Wi-Fi from corporate traffic, IoT devices from user devices. SD-WAN solutions also often integrate with third-party cloud-based security services like secure web gateways, SWEs, from vendors such as Zscaler, Palo Alto Networks Prisma Access, or Broadcom Symantec. This allows you to route internet-bound traffic from branches directly to these cloud security services for advanced threat inspection, URL filtering, and data loss prevention, rather than backhauling all internet traffic to a central HQ firewall. Advanced perimeter security might also involve integrating with next-generation firewalls, NGFW, unified threat management, UTM platforms, cloud access security brokers, CSB, for securing cloud app usage, or network detection and response, NDR tools for behavioral threat analysis.
Wow, lots of integration points there.
All about layers. Seventh, don't forget backdoor security. Attackers might try to exfiltrate data using seemingly innocuous protocols like DNS, use security tools perhaps based on behavioral analytics that can detect abnormal DNS query patterns indicative of tunneling or data leakage. Eighth, compliance is often a major driver for specific security controls. Does your organization need to meet regulations like CIPA, Children's Internet Protection Act, requiring content filtering, or handle controlled information requiring FIPS 142 validated cryptography? Your SD-WAN solution and configuration must support these specific compliance requirements. And finally, consider advanced topics like IoT security. IoT devices often have primitive security capabilities. Use SD-WAN features like microsegmentation to isolate IT traffic onto its own network segment with strict firewall rules, limiting its ability to impact or be impacted by other parts of the network. This is crucial for configuring network connections, services, security, and management tailored to specific device types and risk profiles. Hashtag attack 6.2 business implications.
That's a really comprehensive look at SD-WAN security best practices. It really emphasizes that SD-WAN isn't just about routing agility. It's a platform that needs careful security design. But let's pull back again to the broader business view. What does SD-WAN ultimately deliver for an organization? How does it really impact the bottom line or help achieve wider strategic goals?
From a business perspective, the implications of adopting SD-WAN are significant, and they really tie together many aspects of the design, integration, selection, and implementation of communication solutions that your BCIS All-Stream 47 course covers. First, it usually delivers enhanced performance for critical business applications, especially cloud-based ones like Office 365, Salesforce, or custom SaaS apps. By intelligently steering traffic over the best available path in real time, SD-WAN significantly improves the user experience, which directly translates into increased productivity, better customer satisfaction if customer-facing apps are involved, and reduced frustration. Second, as we just discussed, it can dramatically boost security by integrating robust layered protections across the entire distributed network edge. This includes things like integrated firewalls, segmentation, secure web gateway integration, and centralized policy management. This helps mitigate business risk from cyber threats and potentially simplify security operations compared to managing disparate security tools at each location.
Better performance, better security. What else?
Third, it offers much greater choice and flexibility in how businesses connect their locations and extend their networks to the cloud. They can leverage cost-effective broadband internet and LTE connections more effectively, reducing reliance on expensive private MPLS circuits where appropriate. This agility is crucial for supporting digital transformation initiatives, enabling rapid deployment of new sites or services, and adapting to changing business needs. Fourth, SD-WAN typically simplifies WAN operations through centralization and automation. The centralized controller provides a single pane of glass for managing potentially hundreds or thousands of sites, pushing out configuration changes and security policies consistently, and providing visibility into network performance. This reduces the chance of manual configuration errors, lowers operational costs associated with managing complex traditional WANs, and frees up IT staff for more strategic tasks. So ultimately, S1 helps organizations design more effective logical and physical network infrastructures tailored to modern application needs.
It allows them to configure network connections, services, security, and management with a focus on efficiency, user experience, security, and resilience. It empowers businesses to build more agile, secure, and cost-effective wide-area networks that are really essential for succeeding in today's hybrid work, multi-cloud world. Understanding these business implications is just as important as the technical details, especially as you prepare for industry roles in those certification exams.
Wow, what an incredible deep dive today. Seriously comprehensive. We've really journeyed from the absolute bedrock, the foundational importance of network documentation, all the way through the intricate dance of BGP, understanding its role as the Internet's grand coordinator. We explored the critical strategic thinking behind choosing routing protocols like EIGRP, OSPF, and maybe even BGP internally. And we wrapped up by understanding how modern solutions like VPNs and SD-WAN are fundamentally shaping today's secure, high-performing wide-area networks. I think you, our listeners, should now have a much clearer picture of how these complex systems function, and maybe more importantly, a structured approach for how to troubleshoot them when inevitably things do go sideways.
And remember that initial question we posed about those digital highways hitting a roadblock. Hopefully, the insights we've shared today give you the knowledge and the tool set to not just identify those roadblocks when they appear, but to strategically analyze them and clear them effectively. It's all about ensuring that constant, reliable flow of information that powers our completely interconnected world. These skills, this understanding, they're absolutely essential, not just for doing well in your BCIS 1347 course there at Tarleton State University's Dr. Sam Pack College of Business, but for building a truly resilient, adaptable future in pretty much any business or IT career path you choose.
Absolutely. And if this deep dive has sparked your curiosity, maybe given you that aha moment about how this all fits together, please do us a quick favor, like this episode, subscribe to the deep dive for more insights like this, and maybe share it with a friend or colleague who's also on their own tech learning journey. Your support genuinely helps us continue bringing these valuable discussions to you. And one last reminder, don't forget to check out the description below for those valuable extra resources.
And maybe just a final thought to leave you with. Think about the immense impact that a single, well-placed configuration line or a well-understood protocol behavior can have on a global network connecting thousands of people. And think about how understanding these underlying principles, the why behind the what, transforms you from just a technician following steps into a strategic architect of connectivity, someone who can design, build, and maintain resilient systems. Remember, strong connections aren't just technical, they're strategic. Until next time, keep your packets clean and your networks resilient.